Hello and welcome, guys, for today's session on grade 10 physical sciences. Today our focus is on types of chemical bonds. It's a very interesting session because it has a lot to do with matter and materials, which we did in the previous term. Now, our core focus today is to look at the type of bonds. It's a very interesting section. However, there's quite a lot to do, but we need to pay careful attention to the detail, and also it will again call upon us to recall some of the concepts that we have attempted or done or interacted in the previous term. Right, let's get started, and just to get an overview of what exactly is going to unfold in today's lesson. Hopefully we enjoy it. Let's go for it, guys. Right, okay, as you can see, this is our layout in terms of the overview for today's lesson. Remember, the building blocks of all matter, which are atoms, these are the ones that are actually involved in the bonding. We'll go to the nitty-gritties of what atoms are, how atoms exactly are involved in the chemical bonding. Right. Remember, atoms represents elements. Elements, you know, you can mention your hydrogen, you know, your chlorine, your silver, and the list goes on as far as the periodic table of elements is concerned. Hence, the periodic table will become a very important part of today's lesson. Remember, when atoms bond, they form compounds. Compounds, these are your substances that consist of two or more elements that are chemically joined together. You would have done this maybe in grade 8. You remember that you distinguish elements from compounds, that compounds are made of elements. However, we need also to have a clear distinctions as far as molecules are concerned. Remember, we can have molecules of compounds as well as molecules of elements. If you check, for example, oxygen is an element which consists of two atoms that are chemically joined. So, but these are of the same kind. So these are the elements of the same kind, right? And then if you look at carbon dioxide, carbon and oxygen are elements of different kind as well. Right. We shall also look at chemical formula. Remember, as we talk about water, for example, which consists of different elements, this is an example of a chemical formula in terms of identifying the substance as far as which elements actually make up that particular substance. In this case, carbon and oxygen, they form a new substance if they bond together in that way. And then as a result, we know that carbon and oxygen, when they bond, they give us carbon dioxide, of which it comes from the constituent elements. And then it brings us to the three types of chemical bonding, right? And the big question that we shall focus on today is, why do elements bond? Why do atoms of elements bond? Why do atoms bond? So by the end of today's session, we need to be in a position to explain as to why bonding takes place. Now, the three types of bonding: one, it's chemical covalent bonding. There's also ionic, and then the third one, which is metallic bonding, which is very, very important for us. By the end of the session, this is the bigger scope of today's lesson. Right. Having said that, I think now we get a clear picture as to where exactly we're going with this. So as a result, we'll take it one step at a time and see how at the end of the day we can link these concepts. Once we can establish those key links, I think learning would have taken place. Right, let's go straight to the first section, sub-theme. Right. Now, the periodic table, like I indicated, becomes a very important aspect of of today's lesson. I would think of the periodic table as the Bible of our chemistry, because there's nothing that we can do. As you can see, there are 18 groups in total, and the groups, these are the vertical columns. You know, they represent the groups, like, for example, group 13, group 18, group 1, group 2, you know. So these vertical columns, they represent the groups, right? They represent the groups, okay? Right, and then the horizontal rows, take for example from potassium, calcium, going in that direction, then we've got what we call the periods, right? So just to remind each other of what the periodic table entails. Also, it's very important that these elements that are in group 1, take for example hydrogen, lithium, sodium, they have something that is common as far as their position in the periodic table is concerned. We'd realize that those elements that are in group 1 have got 1 electron at the highest energy level, which is something that we're going to interact with. As you go across, the number of electrons at the highest energy level increases, except for the D block. Now, this is the D block that we're talking about, right? Which it consists of what we call the transition metals as far as classification of elements is concerned. So these are the transition metals. Now remember, most of these substances in the groups have got their own specific names. Let's say, for example, the group 1s, we refer to them as alkali metals. Group 2, they're alkali earth metals. Then we've got the D block, or what we call the transition metals. And then as you go further to the right, group 13 has got 3 valence electrons. You need to pay careful attention to that. And then group 18 has got 8 valence electrons. Electrons at the highest energy level are the ones that we refer to as the valence electrons. So helium, these are your halogens. So this group consists of what we refer to as halogens, right? But remember, the left side of the periodic table consists of metals, and then we've got the transition metals, but as you go further to your right, you have got non-metals, right? Okay, now let's move next and check the key concepts for today. Now, we have what we refer to as the Lewis diagrams. Remember, bonding, when bonding occurs, the electrons at the highest energy level are the ones that take part in the bonding. So as far as the Lewis diagram is concerned, it's an atomic model. In other words, it's a simpler way or an easier way, of representing electrons in terms of their makeup, your nucleus, your electrons that occupy the orbitals. And because we are so much interested in the electrons, that's why we would use the Lewis diagrams to show how the electrons are configured or are laid out, in an atom of an element. So for that reason, so let's think of the Lewis diagram, or sometimes we refer to it as the Lewis notation. It's a standard way of representing atoms of element. So the reason why we want to have a brief look at the Lewis diagram, because as far as bonding is concerned, we use quite a lot of Lewis diagrams to illustrate that. Now, only the valence electrons. Now, valence electrons, that's another key concept for today. When we talk of valence, we're talking about electrons at the highest energy level. Electrons at the highest energy level. Right, so these are your valence electrons, right? So we use the dots and crosses. Let's take, for example, neon, right? If I can take you back a bit to your periodic table, and let's look at neon quickly. If you look at neon, there is neon, it's element number 10, so that's the atomic number, right? So neon has got 10 electrons. So if you could look at neon, for example, it has 10 electrons. So if we can use the SP notation, because neon has got 10, it says to us that the 1s has the what? Has 2 electrons, 2s, 2, 2p, 6. Now, the highest energy level is the second energy level, which has got the suborbitals, the 2s and the 2p. Now, if you check, neon is completely filled. As a result of that, now the valence of neon is the number of electrons at the highest energy level. The highest energy level is the 2s and the 2p. So the valence is equals to 8, right? That's why it occurs in group 18. So group 18, the 8 suggests the valence. Okay, right. Now, in other words, we're not going to show the 1s2 because they are not directly involved in the bonding as a result of that. So if I could use the dots and the crosses, I would say 1, 2, 3, 4, 5, 6, 7, 8. So this is the typical Lewis notation for representing neon. It only shows 8. However, it doesn't necessarily mean there are 8 electrons. It means at the highest energy level, there are 8 of them, which shall be of interest to us as we look at chemical bonding. Now, helium is another element which is in group 8, but it's a special one because, remember, helium is just 1s2. In other words, what that says is that at the highest energy level, it has got 2 electrons. So that's why it's in group 8 in the sense that it's completely filled, right? So helium will have your 1, your 2. So these are the typical Lewis notations. Now, if you can look at a different example, say oxygen, it is in group 16. Now, in other words, what it means that it has got 6 electrons at the highest energy level. So we can use dots for a change because remember, the Lewis diagram consists of dots and crosses, right? So we can use either of them. Now, 2, 3, that's 4, that's 5, 6. So this is the Lewis notation representing oxygen. For hydrogen, just 1 because it has got 1 electron at the highest energy level, group 1. The same goes for sodium. Now, if you check, these two are in the same group because they are completely filled. Now, that's why we call it group 18. Right? This is 8. Helium is an exception. We need also to mention that. Now, as far as sodium is concerned, there's 1 valence electron. Hydrogen is 1 valence electron. So if we go back to our periodic table, you'd realize that hydrogen and sodium, they're in the same group because of that particular property. Right. Now, going back to the Lewis notation is very key. I think we can even do the same for chlorine. Chlorine is in group 17. Now, 17 suggests that there are 7 valence electrons. So 1, 2, 3, 4, 5, 6, 7 of them. So these are the typical Lewis notations. Right. Now, having said that, I think the Lewis notation will be our standard way of representing the electrons, which is very key for us to have a clear understanding that it only represents the electrons that occupy the highest energy level. Why are we so interested in the high energy level electrons? It's because these are the very electrons that take part in chemical bonding, which is the core focus of today's lesson. Right. Now, the big question is, why do atoms bond? That's the big question for today, or the big idea. At the end of the lesson, we need to have a clear idea as to why bonding takes place. So that's our big idea for today, right? Why do bonding take place? Now, remember, atoms have got charges. Now, obviously, there will be attractive forces between the nuclei. The nucleus is your nucleus, which contains the protons as well as the neutrons, right? And these are not necessarily involved in the transfer as far as bonding is concerned, or the sharing of electrons, as we shall establish at a later stage. Now, and the electrons of the other atom are stronger than the repulsive forces. That means it says the electrons are kept intact by the nuclei. The nuclei is the plural for nucleus, right? And then the core reason why electrons bond is because of stability. We refer to group 8 elements as noble gases, inert gases, stable gases. The word noble and inert suggests that they are generally unreactive. They are less willing to give electrons. They are less willing to accept electrons. At the same time, they're less willing to share electrons at the very least. So when these atoms bond, the idea is to have an electron structure that resembles that of group 8 elements, which has to do with stability. So when we refer to stability, we're saying stable gases, right? We're talking about stable gases which are in group 18, right? Group 18. So group 18 completely filled, right? So we shall establish that only the valence electrons are the ones that are involved in the chemical bonding, which is the key thing for today's session, right? Now, moving along, in the periodic table, if you can check, let's say, for example, we're referring to fluorine. Fluorine has got 7 valence electrons because it is in group 7. So as a result, for it to have an electron structure of a neon, which is the adjacent, what you call element in group 8, it will either have to, in essence, it actually has to gain a single electron to form a neon, right, which is very key. So the periodic table will be very much an important tool in terms of understanding why bonding unfolds or occurs in the very same manner that it does, right? Okay. Now, having said that, I think it will be also important that without the understanding of the Lewis notation, it becomes somewhat of an obstacle of some sort for us to understand the bolts and nuts of chemical bonding. Having said that, Lenos, I think we need to take a short break, then we'll delve deeper into the types of chemical bonding after the short break. Cheers, see you after that, guys. Welcome back, guys. After a short break, as we're saying, we're looking at the different types of bonding, and we've emphasized that the valence electrons that are depicted or shown in the Lewis diagrams will become an important aspect of our lesson today, that because these valence electrons, or the electrons that tend to occupy the high energy level, are the ones that are directly involved in the chemical bonding. Let's look at the three types of bonding now that are involved as far as substances are concerned. Right. Now, the first one is covalent bonding, right? This which occurs between nonmetals. Now, nonmetals are generally more to the right of the periodic table. These are to the right of the periodic table, right? Now, if we talk about to the right of the periodic table, we're talking about elements like carbon, your oxygen, your sulfur, these are the type of elements which I would classify as nonmetals, right? Having said that, these are the ones that are involved in covalent bonding. The word valent suggests something about valence electrons. It suggests something about the valence electrons, right? Now, why is it so important to us? Is because these are the very electrons that are involved in chemical bonding, right? The second type of bonding is the ionic bonding. Obviously, this involves ions. We shall talk about them. This occurs between cations formed from a metal. Metal, take for example, potassium, right? And if potassium, which is in group 1, wants to have a stable electron configuration, remember, it has got only one valence electrons, and the underlying energy levels are completely filled. So it would rather lose that that electron. So once it loses that electron, what actually happens is that it becomes potassium becomes what we call a cation, right? So the metal would rather use and form what we refer to as a cation, right? Now, when it bonds, let's say, for example, with chlorine. Chlorine is in group 7. It has got how many valence electrons? 7 of them. 1, 2, 3, 4, 5, 6. Okay, 7. Now, for chlorine, it will have to accept an electron so that it looks like argon or the next element, as we shall establish from the periodic table. So if we include another electron, say from potassium, this one has got one extra electron, so it forms what we call a negative ion, which we refer to as an N ion. So the two ions that are involved in ionic bonding are called cations and anions. The cations are for the metal, right? And then the N ion is obviously for the non-metal. Chlorine is one example of a non-metal, right? So this is a non-metal. So emphasis is put on the fact that ionic bonding only takes place between metals as well as non-metals. We shall establish how it exactly happens. Then as far as metallic bonding, this only happens between metals. Metals, we are referring in this case to more particularly the transition metals. So if we talk about transition metals, you remember very well that as far as transition metals, we're referring to metals like your copper, your zinc, your aluminium, your your gold, these are your typical elements that would be directly involved, or typical examples of what would refer to as the metal. So for that reason, we would think of metallic bonding only occurring between atoms of metal substances. Right. Let's look at the first type directly now. Now we want to show the ionic bonding as to what exactly happens. Now, this is the Lewis diagram for sodium. If you look at sodium, it has got 1 valence electrons. Remember, the word valence is a lot to do with the Lewis diagrams, because it doesn't mean there's only 1 electron. There are more electrons than that, but at the highest energy level, only 1 of them. So ionic bonding has a lot to do with the transfer of electrons. Remember, transfer occurs between a metal and a non-metal, okay, and a non-metal. In this case, the non-metal is chlorine and the metal is sodium. So there is transfer of electrons. So what actually happens, you'll have this electron being transferred there, so that this chlorine has an electron structure that is similar to group 8, because if we include it here, now we don't necessarily have it in the sodium, right? In the sodium. So if we don't have it in the sodium, it means sodium will form what we call a cation. Remember, it's the metal which forms the cation in this case. So it's a positive ion, which electrostatically is charged. It means it has more protons than electrons. Now, as far as the chlorine is concerned, we'll have the Cl, and then we have the original dots to represent the electrons that originally belong to chlorine. Then the extra one, which is a cross. Remember, this is a dot cross diagram in terms of the Lewis notation. So this is a dot cross. Now, this one now is formed what we refer to as an N-ion. So now the N-ion is negatively charged. Now, there is a force of attraction that exists between the positive cation. Now, this is the cation, the cat for positive, and then the N for negative. Now, the N-ion for negative. Now, what keeps these together is the different charges or between the two particles. Now, we refer to them as ions. They're no longer atoms. So they have got what we call electrostatic forces keeping these two ions together. So this is the electrostatic force. Sometimes we refer to it as the Coulombic forces. Right, we could refer to it as the Coulombic forces. Now, as a result of that, we would have our substance NaCl. Now, in other words, 1 atom of sodium is involved with 1 atom of chlorine. Hence, this will be our chemical formula, something that we referred to earlier on. Right, which is very, very important. Right, let's move on and look at the nitty-gritties of ionic bonding. As I've illustrated in that typical example, it's very important for us to know that as far as ionic bonding is concerned, the metal loses the electron to a non-metal. Now, in that process, when the atom, the metal loses the electron, it becomes a cation, and then the non-metal becomes a N-ion. Right. So the bonds formed between those two metals through the transfer. Transfer, it means to lose completely. So if we transfer, sodium loses, and then chlorine will obviously gain. So that is the net transfer. It means that one would sodium will have more protons than electrons, whereas the chlorine will have more excess electrons alternatively. Now, the positive ion, that's the cation. We also spoke about the electrostatic forces, which are the Coulombic forces, right? Coulombic forces, okay, which is very, very important. Now, the difference in electronegativity is more than 1.7. Now, these are very, very ionic in terms of the difference in terms of the charge. One is more positive and the other one is more negative. We would have spoke about ionization energy. Because sodium has a tendency to lose, electrons, so when it loses the electrons, it becomes a positively charged ion, which is a cation, and then the electron that it loses is the one that goes to chlorine. So these metals tends to have a low first ionization energy. So the energy required to remove that electron which is transferred, right? Now this, it means that, in other words, nonmetals also have a tendency to accept. So there is loss, giving away, as well as accept, which entails what we referred to as the transfer, right, which is also very important. Now, if you look at this ionic structure, you see now these are the Coulombic forces that keep these ions together. So that is our N ion, the chlorine is our N ion, right? And then that's our cation. So the forces that keep them together are those electrostatic forces or the Coulombic forces. Right. Let's look at the periodic table again, just for the sake of reference. There is sodium. It has got 11 electrons with 1 electron at the highest energy level. There is our chlorine. It is in group 17 with 7 valence electrons. So when sodium loses an electron to become Na+, what would happen is that it will have an electron structure similar to that of neon. Right. Whereas if chlorine gains, it will have an electron configuration that resembles that of argon. As a result, there is what we referred to as stability. Right. Okay. Now, let's look at the other type of bonding, which is also very important, which is the covalent bonding. Co, it means to share. Now, this has a lot to do with the sharing of electrons. Right. Sharing of valence electrons. To achieve stability, so that there is stability. If you look at the molecule of hydrogen, each one of them is in group 1. These are of the same kind. So here it will be a molecule of an element that will be formed once they bond with each other. Now, remember, hydrogen wants to have an electron structure that resembles that of helium. So for that reason, what's going to happen is that they would rather share than give to each other. So if we bring this, this hydrogen closer to the other one, what would happen there? It means that they would share that pair of electrons. Once they share that pair of electrons, both of them are now stable. Then a molecule of hydrogen consists of 2 atoms of the same kind. Hence, we write it as H2. Right. So that's a simple example as far as covalent bonding is concerned. Now, if you look at this one, a hydrogen wants to look like William, and we've looked at chlorine before. Chlorine wants to have an electron structure similar to that of argon. So what's going to happen is that they would rather share, so that if they share, each one of them, the shared pair of electrons belongs to the 2 of them, or would rather even put them like that, and then just by indication show that this will be a shared pair of electrons. And what has happened here, it's a single bond because a pair of shared electrons exist between the 2 atoms of the different kind. Now, this hydrogen chloride molecule consists of atoms of different kind, hence we write it like that in terms of formula. It's usually a gas. Now, for that reason, there is 1 atom of hydrogen as well as 1 atom of chlorine when this type of bonding occurs. Right. Now, let's look at the key concept as far as covalent bonding is concerned. This happens between 2 nonmetals. Remember, nonmetals occur to the right or further right of the periodic table of elements. Right. Now, if you come to think of it, we have got hydrogen is an exception as far as alkali earth metals are concerned. You think of it as a non-metal. It's in group 1 by the virtue of the fact that it has a valence of 1. However, it's not classified as a metal as such. And chlorine is also in group 7 or 17 rather, with 7 valence electrons. These are examples of what? Non-metals. Okay, so covalent bonding will only take place between molecules, also atoms of nonmetals. Right. Now, these they share. The key thing is to share. The word co means to share. Right. Then valent means electrons at the highest energy level. Now, molecules form as a result of covalent bonding. So the substances, whether it's an element which is diatomic or triatomic, let's take for example O2. There is covalent bonding between these 2, but these are atoms of an element. But if you look at HCl, this is a molecule of a compound. We need also to clarify that as well. Right. Now, the overlapping of orbitals, it means that these atoms of bonding, which are actually share the electrons, get to be close enough so that they can get a single bond. Is only when a single pair of electrons is shared. Double would be obviously 2. Then would also represent them in this way. Say, for example, the between carbon and oxygen would have something like that. This is a double bond, meaning that there is a shared pair of electrons between these two atoms, right? The polarity has a lot to do with the electronegativity of substances. Now, polarity, it means there is a net charge, based on the tendency to attract the bonding pair of electrons. So that particularly has to do with the classification in terms of molecules being more one atom being more electronegative than the other. Right. Having said that, there is also the last, which is also very important, the metallic bonding. As the name suggests, metallic, this only happens between metals. Only between metals. We've mentioned transition metal as a perfect example of elements that are actually involved in metallic bonding. So the name itself of this type of bonding actually is self-explanatory. It explains itself already because it only happens between metals. The idea between these behind metallic bonding is that the atoms of in this case of the same kind, they tend to be closer together, and these are what we call delocalized electrons. If something is delocalized, it means it is free to move. And these electrons, or we think of it as a sea of electrons that are free to move between adjacent nuclei of atoms of the same kind. As a result, there are those forces that keep them together, So this is a special type of bonding where there is a positive core. So we'll think of this as a positive core in a way, but remember, these electrons are moving very fast between adjacent nuclei of atoms. As a result of that, we'll have the smallest particle being the positive ion, which only occurs in metals only. Right. Having said that, I think the three types of bonding, they differ in many ways than one. So for that reason, I think we need to have a clear distinction between covalent, which is the sharing, the ionic, which has to do with the transfer, and then the metallic bonding, which only occurs between metals, particularly the transition metals. Right. I think we've digested quite a lot now. Before we go to the practical activities as it is the norm, I think we would also take a short breather, and then when we come back refreshed, we shall look at the problems and the feedback and then consolidate. See you after the break, guys. Hello, guys, and welcome back to the last segment of our session today, chemical bonding, which I find very interesting in the manner that there are quite a lot of things that we've discussed, or concepts rather, which somehow have a lot to do with the periodic table. So we want to very much appreciate the fact that the periodic table becomes a very useful tool in terms of chemical bonding. Right, let's quickly look at the questions, and then I'll give you time to attempt that. Then we shall do our feedback as a collective and see how best we can respond to these type of questions. Right. The first question says, in each of the following cases, predict. So prediction is a skill in science. The type of bond that will be formed. In each case, I'm going to give you, say, 3 minutes to attempt that. Then we shall consolidate and see how best we're supposed to respond to that. All the best, guys. 3 minutes. There you go. All right, guys, having attempted the first question, which has a lot to do with identifying your type of elements that are going to be involved in the bonding. Remember, we've got metals, non-metals, as well as semi-metals. But in this case, if you look at iodine, iodine is a non-metal as well as hydrogen. So the most probable, because if you look at hydrogen, it's going to be just 1 valence electron, and then iodine will be 7 valence electrons because it is in group 17. So the periodic table becomes very relevant in this case. So what would happen in this case is that there will be the sharing of electrons, given the fact that these are non-metals. Then the sharing, it takes us to definitely this is covalent bonding. Right, let's look at the same, it means here these two are your non-metals, so this definitely is going to be covalent bonding, because we emphasize the fact that covalent bonding takes place between non-metals. This is for non-metals, right? So the two metal elements involved are non-metals, hence it will be your covalent bonding. Right, moving to the second question, sodium is a metal, sulfate ion. The sulfate ion, if you recall from chemical formula in the first term, we said the sulfate ion is SO4 2 minus, and then when sodium bonds, remember for sodium, which has a valency of 1, when sodium bonds, and valence has a very low ionization energy, it forms that positive ion. So this is a cation, right? And the sulfate ion is an anion. And obviously, because these are ions involved, it will take us to ionic bonding between the two ions. Right, let's look at number 3. Zinc is a transition metal. So between metals of zinc, this is a transition metal, hence between atoms of the same kind, what would happen is that we would have our metallic type of bonding, where the zinc atoms become the nuclei, and then the electrons, which are delocalized, move between the adjacent nuclei, which is positive, the nucleus, as far as protons and neutrons. So you'll have a sea of delocalized electrons, hence would refer to this as metallic type of bonding. Then chlorine is a typical non-metal, but now the catch is that these are atoms of the same kind, right? So when chlorine, which is a non-metal, they bond with each other, what would actually happen is that they would share electrons. So the sharing takes us to what we referred to as covalent bonding. But the molecule that will be formed, it will be a molecule of an element. So when covalent bonding takes place between non-metals of the same kind, just like between oxygen, we get, for example, Cl2. These are 2 atoms of chlorine, which share a pair of electrons. When they share a pair of electrons, from our Lewis notation, we would understand that what will be formed here is a molecule, but this is a molecule of an element. And then the fifth one, it says ions. That's the key emphasis. I think we need to underline the keywords. Now, the potassium, which is in group 1, which is a metal, potassium is a metal. Now, and then the permanganate ion is a typical complex ion. You must know the formula, which is MnO4 minus. Now, when they bond with each other, it means because potassium wants to be like group 8, it would rather lose the single valence electron that it has. So once it loses that single valence electron, what would happen is that it will form a positive ion, which we refer to as a cation. So obviously, ionic bonding will be very relevant in this case. Right. Having looked at that, I think the key thing was the periodic table as far as the classification of elements. You need to know your metals, your non-metals, whether to determine whether it will be the transfer or the sharing. But now, if it's the transition metals bonding with itself, another transition metal of the same kind, atoms of the same kind, then it takes us to what we referred to as metallic bonding. Right. Let's look at the next question very quickly, which has to do with the Lewis diagrams. Emphasis is on that to show the type of bonding in each of the substance. I'll give you 3 minutes to attempt each one of those questions, a minute for each, and then we'll do the feedback. The key emphasis is the Lewis diagrams. Let's go for it, guys. All right, guys, hopefully you've made your attempt on the three compounds or substances that I gave to you. Let's quickly have a look at how the Lewis notation can be used to represent the type of bonding in each one of the three substances. Right. Now, the first one is calcium chloride. Right. Before we understand, we understand that the fact that there is calcium and chlorine involved. So if you go to calcium is Ca, and it is in group 2. It means it has a valency of 2, right? And then chlorine is in group 7 or 17, rather, it means that it has got 7 valence electrons, right? Now, chlorine wants to be like argon, and calcium also wants to be like argon. Now, remember, argon is 18, so calcium will need to lose electrons because it's a metal and a non-metal. So the metal has a lower ionization energy, so it will transfer that electron to your chloride ion, the chlorine atom. So remember, now there's an extra one. It simply means that for calcium chloride, we need 2 of the chlorine atoms in that case. Then the 7, it means then we'll transfer the other one to the other chlorine. For that reason, we would end up having a case where we have the chlorine, because calcium has lost 2 electrons, then it becomes Ca2 plus, right? And then one chlorine becomes Cl minus, and the other one becomes Cl minus. So there has been a transfer of electrons because this is ionic bonding. For that reason, then we would have our calcium chloride having only 1 atom of calcium and 2 atoms of chlorine. Right, so that's our ionic compound, or which we refer to as a salt at times, because that's what happens when ionic bonds are formed between substances. Then for carbon dioxide, so obviously there's carbon and 2 oxygen, right, atoms. Carbon is in group 4, it is a valency of 4, right, and then oxygen is in group 6, it means it's valency of 6. Remember, we said the periodic table becomes a very, very important part of our lesson today, in the manner that we always want to refer to the periodic table. So it has got 6, 1, 2, 3, 4, 5. Then we've got the 6th one, 1, 2, 3, 4, 5, 6. Right. Remember, carbon is a non-metal, oxygen is a non-metal. So we're obviously going to covalent. They shall be sharing. Each one of them needs to completely fill themselves so that they can be stability, as we referred to it earlier on. Right. Now, they would share the pair of electrons, but if they share this pair, what would exactly happen now? This shared pair belongs to both. Now carbon is 5, chlorine is 7. They'll share another pair. Now this oxygen is stable, this carbon is not stable. So they share this other pair again and share another pair. Now if you realize that 1, 2, 3, 4, 5, 6, 7, 8. Now this oxygen has got 8, the other oxygen has got 8, and as well as the carbon, 1, 2, 3, 4, 5, 6, 7, 8. Now, this is the formation of carbon dioxide using the Lewis notation. But what is very important is that there is a double bond that has been formed between atoms of carbon and oxygen. So the double bond there is very important because there are 2 pairs of shared electrons. Then we have got ammonia. Where do we start as far as ammonia? We need the formula of the substance. Now, if ammonia is NH3, these are some of the common substances that have got a wide range of everyday uses. It is for that reason that we want to have a clear understanding as to how bonds are formed between ammonia. Ammonia is used as a disinfectant, as a cleaning agent in most of our domestic detergents, if you want to refer to it. So as far as ammonia is concerned, there's nitrogen. Nitrogen, which is in group, if we can go to our periodic table, nitrogen is in group 5, right? So it means it has got 5 valence electrons, right? It has got 5, I'll extend the page. It has got 5 valence electrons. And then hydrogen is in group 1. Each one of them has got 1 valence electron, right? So meaning that at the highest energy level, each hydrogen has got one valence electron, which happens to be the only electron anyway, right? Now, then there's another hydrogen. There are 3 of them. So for hydrogen to achieve stability, it needs to have another pair of electrons so that it could look like helium, because bonding has to do with stability. So that will be a shared pair of electrons between a nitrogen and hydrogen. So this hydrogen is stable because it has got 2, but the ammonia is not yet stable because it only has 6, right? Then 7 with that hydrogen, right? Using our dot cross notation, and then now it has got 8. Each one of the hydrogen atoms are stable. For that reason, this has been the sharing of electrons at the highest energy level. Hence, in ammonia, in a molecule of ammonia, this is a covalent type of bonding. Right, this is a covalent bond. So again, that's why we said there's a single nitrogen atom and 3 hydrogen atoms which bond with each other. Right, I think we've said quite a lot for today. The key things, maybe what is it that we take home after all has been said and done? Let's remember there are 3 types of bonds: ionic, covalent, and metallic. The covalent sharing, ionic transfer, metallic only happens between atoms of a metal substances. Right, I think it has been indeed a very interesting session for today with our practice activities to consolidate that. I think from now, myself, Temba Ngube, I think we shall call it a day for now. Hopefully we'll see each other in the next session again. Cheers and bye, guys.